Okay, so we're talking about intermolecular forces. Are you guys familiar with intermolecular forces?
It sounds familiar. I just can't really remember it.
You guys did a lab already dealing with it, sort of?
Yeah.
It was the slime lab. Okay, so we'll get started on it while everybody else creeps in. So dry ice, right? So if you guys take a piece of dry ice and you blow on it a little bit, what happens?
The steam, smokes.
So vapor starts coming off. Okay, does it turn into a liquid?
No, more of a gas.
It's a gas. Okay, so you basically go from the solid state to a gas state. You don't see that transition to a liquid state, right?
Mm-hmm.
Why is that? Or why do you think that's the case?
Is it
That is true. Is it due to intermolecular forces? Yes, it is due to intermolecular forces. That is correct. Intermolecular forces plays a huge role in that. So determining whether things are going to be a solid or liquid. So what is that term, intermolecular? Let me type it on the board. Can you guys see my slides? You see my beautiful test tubes?
Yeah.
Okay. So,
Like, yeah, like in between what you can't see.
and then we have another term, intermolecular forces. Yeah, between molecules. Okay, yeah, so it does mean between molecules. Good job, Mauricio. So it means between molecules. So the interaction or the forces that are involved between two different molecules. Okay, so when we think about water, right? Well, you're going to say something?
So like bonding, does it have to do with bonding?
Not bonding. Bonding would be, well, okay, so I'll rephrase that. Certain times with bonding, it'll count, but it's not really bonding. But bonding is intramolecular. Okay, so let me kind of clarify that. So we got intermolecular and intramolecular, right? So say we're looking at water, H2O. The bond between oxygen and hydrogen, that would be your intra. Intra meaning like intrastate, within the state, right? So it's within the molecule, okay? Inter, like if you think about interstate, what do we know about interstates?
they go through multiple states?
They go through multiple states. So like between states, right? So in this case, it's between molecules. So in this case, it would be the same thing as looking at water, but between two water molecules. Right? We know that water is a polar molecule, so it has a partial positive and a partial negative moiety, right? Or a pole. And then, so if we have two water molecules, what's going to happen when the partial positive gets close to the partial negative?
They're attracted to each other?
That's right. And you're going to get attraction, right? And so they're going to interact with each other. These guys are going to form what we call a hydrogen bond. And we draw a hydrogen bond because it's not a real bond, but it's those partial charges interacting, that positive and a negative partial charge interacting with each other. It's not as strong as an ionic bond, which is a complete positive and a complete negative interacting together, right? So
I thought hydrogen bonds are like super weak.
they're weak,
Right.
yeah. So they're not as, like I said, they're not as strong as ionic. Ionic is stronger, but hydrogen bonds, that if you get a lot of them, right, a whole bunch of them, they're kind of good. So have you guys ever played Red Rover, send Jamie right over, right? And you guys run through somebody's arms,
Yeah.
right? Okay, so imagine we're doing this with fist bumps instead of holding each other's hands. And let's say me and Michaela were fist bumping each other. And Alex was going to run through. Now, just me and Michaela fist bumping each other, is that going to slow you down?
No.
No, it's probably not going to slow you down. But if we had a whole bunch of people lined up together, fist bumping, just pressing it, that's going to slow you down. You're not going to make it all the way through because you're not going to have enough energy to pull through all of us. So it's like an additive force to each one. So each fist bump is going to add another layer of a force, right? And so you can get a whole bunch of those to make it really, really strong, or strong enough to sit there that you have to put a whole lot of energy in to sit there and break it up. Does that make sense?
Yeah.
Okay.
So like water's surface tension would be an example of the intermolecular forces.
That's right. Water surface tension. Exactly. Yep. Yeah, so that is a perfect example of intermolecular forces. Okay. And so again, where intra refers to like the bonds, right? Between them is in the molecule. And then intra is between molecules. Okay. So let's talk about some of these intramolecular forces. And then I'll show you some pictures of them later on. Oh, let's see, clear. Actually, let me, yeah. Board. Okay. You guys see my whiteboard now?
Yeah.
Yeah.
Starting to feel old. I have to ask you guys for everything. Find my glasses for me. Okay, so we'll go from, so far we talked about hydrogen bonds, right? And I'm going to give you a little more of a definition for hydrogen bonds. I can spell hydrogen. Okay, so hydrogen bond, first off, the interaction between it is going to be about 10 to 40 kilojoules per mole. We have, okay, now a hydrogen bond is, you saw it was hydrogen and oxygen, right, that were interacting in water, in the case of water. So when I drew my water molecule, I had that oxygen interacting with the hydrogen that was next to it on another molecule. And I drew that funny looking line suggesting there's interaction between those two, right? So we have this going on, and it's going to be going on continuously throughout all of the water molecules, right? Okay, so this partial positive charge is going to be interacting with this partial negative charge, and it's going to be just because of interaction. Now, this isn't a complete interaction. It is a weak interaction, right? And so this is about the energy that it's going to take to disrupt that interaction. Okay, so it lets us know the strength of those interactions. Okay, does that make sense? Yes, no,
Yeah.
maybe. Okay.
Yeah.
So, and this represents like this is about the energy associated with one hydrogen bond. Okay. So from 10 to 40 kilojoules. So it really just depends on which atom it's going to be interacting with. Like when we take a look at hydrogen bonds, you're going to be looking at hydrogen interacting with nitrogen, oxygen, and fluorine, or fluorine. Okay. So in this case, it's oxygen that it's interacting with. Okay. But that's only when you have a positive charge associated with that hydrogen. Does that make sense? Or a partial positive, not a positive charge, a partial positive charge.
So hydrogen bond is
So-
only when the hydrogen atom is partially positive.
Yeah, so it's when this guy is partially positive and this guy is partially negative. And so it's just the interaction, because those guys are partials, right? They're interacting, but that interaction isn't as strong as an ionic. Okay. And you guys already know about ionic, right? If we have an ionic interaction.
So the 10 to 40 kilojoules you said is like per hydrogen bond.
Yes.
I'm a
So
little bit
it's-
confused about how it's per hydrogen bond, but it's also kilojoules per mole.
Well, it's okay. My apologies. Let me explain this. So it's making reference to the amount of joules for a mole. You're right. So it's moles of hydrogen bonds. But what I'm saying is 10 to 40 by the fact that hydrogen is interacting with nitrogen, right? That'll be your lower end, because in that case, that energy is going to be lower than in the case of hydrogen interacting with fluorine. It's going to take more energy to disrupt the fluorine than the hydrogen interacts with the fluorine than the hydrogen interacts with nitrogen. So you're correct. It should be moles, not.
Okay.
Okay. So if we have an ionic and ionic interaction, typically the low end of an ionic interaction, that's going to be roughly and again, depending on which ion compound we're talking about, maybe about 800 kilojoules per mole. Okay. So we have ion dipole. Let's do dipole first. Dipole. So you guys know what I mean by dipole? Di mean what? What does di stand for?
2.
2, right? So when I talk to you guys about that charge, this guy being partially positive and this guy being partially negative, right? This represents a dipole because the electron is favoring oxygen, is spending more time with the oxygen. So that's why oxygen is partially negative. And then hydrogen is partially positive, is because the electrons are moving towards the oxygen. And so in that case, hydrogen is losing those electrons, or not necessarily losing, but they're not favoring hydrogen as much. They're favoring oxygen because oxygen has a strong pull. Okay, so that is an example of a dipole. So hydrogen bond is essentially a special case for dipole. Does that make sense?
Mm-hmm.
Okay, and so we distinguish between them because we know that, like, for instance, we have sulfur chloride, sulfur dichloride. Okay, so in the case of sulfur dichloride, then we have a dipole situation going on in that case as well too, right? Yeah, no, maybe.
Yes.
So we know the bond between the sulfur and the chloride, who's going to be favored?
Fluoride?
Chloride. Okay, so in that case, the chloride is going to be flavored, right? This is a crappy example, but so then this guy is going to be partially positive. This guy's going to be partially negative, and then the corresponding guy over here, you're going to have sulfur again. You're going to have your chloride here, and these guys are going to interact with each other, and these guys are going to interact with each other. Okay, so that's an example of dipole-dipole. It forms a dipole and is going to be able to interact that way. Okay, and so in that case, the dipole-dipole interaction, that guy is going to be about 5 to 25 kilojoules per mole. Oops. Okay, so when we put salt in water, what happens in the case of salt in water?
The water like pulls apart the atoms in the salt.
Okay, so we have the ion, the sodium, and we have the chloride. So how do they pull them apart?
Because the sodium is attracted to the partial negative on oxygen, and fluorine is attracted to the partial positive on hydrogen.
Okay. Okay, and so this is an example of ion dipole. And this guy is pretty strong, actually, 40 to 600. Mole. Okay, and so when we're talking about carbon dioxide, we're talking about this guy. What's happening in this situation? Is it, first off, is it polar or is it non-polar, this molecule? Because when we're talking about the sulfur chloride is actually considered to be polar because you have those lone pairs, we have that bent structure. And so,
This would be polar. Well, the bonds would be polar, but the overall molecule is non-polar.
that is correct. So the bonds would be polar between the carbon and the oxygen, but overall, it would be non-polar, right? Because they're both pulling opposite directions, so they're going to balance each other out. Okay, so this is a non-polar molecule. So what's going to happen in this situation? Let's say the reason why carbon dioxide does form a solid, although it's a weak solid, is because you do have what we call induced dipole. Okay, and so what I mean by that is that, well, it's, let's see, how to, so have you guys watched Battlestar Galactica? Ever?
I
Anybody?
have not. I've never seen it.
No,
Okay,
no idea.
so this won't be a good one. I'm trying to think of a good example. I know. You know the little, not counting, the pendulums. You've seen a pendulum before, right?
Yeah.
Yeah.
Okay, so does the pendulum spend more time on one side than the other?
No.
No.
So technically they spend the same amount of time on each side, right? As it one side, ding, ding, ding,
Yeah.
right? Okay, so the electrons here are going to act like a pendulum. So what happens in this molecule, because the electrons are going to be pulled in one direction on that oxygen, but the other oxygen is going to have the same type of pull. So then they're going to get pulled back in the other direction. So in the grand scheme of things, nobody's being favored, but they're being induced at moments. So just temporarily, if you catch it at the right time, you can have an interaction. And so we could have two carbon dioxides. Can't think this morning. I can't think this evening, obviously. We can have two carbon dioxides, and if we catch it at the right time, we could sit there and have an interaction because the electrons are being pulled from one oxygen to the other side, from the other oxygen, going through carbon, of course, but being pulled on each side. So does that make sense?
Yeah.
Okay, and so that is an example of an induced dipole. It's induced because it's only temporary, right? And in this case, it's being induced by its neighbor, right? So if we have two carbon dioxides doing it, so this guy would be called what we call induced dipole. Induced dipole interaction. Okay. These are also called dispersion forces. These are also called London forces. And these are also called van der Waals forces, or I should say. Van der Waals was kind of he kind of generalized a lot. And so he included these guys with anything that is induced in general, okay? And so, but that'll be like one of the types of van der Waals forces. We were being very specific on that. So, and so these guys are about, let's see. 0.05 kilojoules per mole. Okay. Let's see.
So, like, if the induced dipole bonds are formed when the electrons are essentially like in a temporary state,
Mhm.
wouldn't those electrons have to remain there for that bond to like continue?
But it's not really a bond. It's not a bond that's happening. Remember, the electrons are moving. Electrons are always moving, right? And so that's what we're kind of playing with, the electrons that are always moving. And so it's an interaction. And no, that interaction isn't going to remain. It's going to loosen, right? So if they're opposite of each other, right? So you have that positive or you have that positive and positive on the same side, they're going to kind of repel against each other. And so if you kind of think about the way dry ice works, right? So if you just blow on dry ice, what happens?
It like vaporizes,
It
right?
vaporizes almost instantly, right? Just
Mhm.
the minimal amount of energy applied to that situation causes it to vaporize. You don't have to even really, you look at it wrong, it vaporizes, right?
Right, right.
Okay. So
Okay. So it's yeah, it's not. I see what you mean. Like it's not a bond. It's just a very weak interaction.
that's right. And so they're not bonded, they're weakly interacting.
Hmm.
Okay. So so we have ion dipole. So we also could have induction by ions, right? So we can induce by the ion as well too. So we can go ion induced dipole. Okay, and this guy is going to be 3 to 15 kJ per mole. Okay, and then we have let's see, dipole induced dipole. It's about 2 to 10 kJ. Okay, so which one are going to be weaker forces?
The induced dipole?
The induced dipole or dispersion forces. Right. So yeah, these guys are going to be weakest. So it's really easy because this represents the energy it takes to dissociate, right? This guy takes very little energy to dissociate, so that's going to be the weakest. Then it's going to be our dipole induced dipole. That one's going to be pretty weak as well. And then this guy is going to be a little bit stronger, but still kind of weak, right? And then the strength goes up as we go up, except although this guy got shifted, he should be up here. Right? So dipole is going to be the next one. Then we have hydrogen bonds. Then we have ion dipole. And then, of course, ion interaction is pretty strong. Right? Okay, questions, concerns, Cash? So, and these guys, the ion interaction is considered a traditional chemical bond, right? So it's an ionic bond. So we know that that guy is relatively strong for anything. So this is like 800 plus, I should say. Because some of them get really, really strong. Okay. Okay. Are there any questions? Simple, not too hard.
So dipole weaker than a hydrogen bond?
A dipole is weaker than a hydrogen bond. Yeah, because hydrogen bond is a special dipole. So it's always when you have hydrogen next to something that's really strong and polar. So that's going to be either, like I said, nitrogen, oxygen, or fluorine. Those are your strongest electronegativity elements, right?
Oh, and a hydrogen bond has to bond to one of those, huh?
It has to interact with one of those.
Okay, yeah.
Yeah. Okay,
Yeah, makes sense.
so any other questions? Everybody's good there? Okay, and so you guys want to remember that this is interactions between molecules, right? Can you guys give me some examples of, let's say, well, we'll start with the ionic interaction. Examples?
Wouldn't it be like the polyatomic ions?
Polyatomic ions, yeah, that's perfect. So we could say NH4, NH4, sodium chlorate. Okay. Okay. So what about ion dipole? Kind of talked about that one. What did I use
Salt.
as an example? Salt and water. Yep. So, or just let's say our aqueous solutions. Let's say salt, water. Okay. Hydrogen interactions, hydrogen bonds.
Water.
Water. Okay. Dipole.
Carbon, or no?
I mean, would it be like carbon dioxide interacting with itself?
Nope. Not carbon dioxide. Carbon dioxide would be an example of
The induced dipole.
induced
Oh, yeah,
dipole.
yeah.
That's what I was gonna say at first, but I stopped myself because I was like, wait, that's the wrong one.
Yeah, I got mixed up too.
Didn't you use like oxygen with hydrogen?
No, that was what I used for.
That would be the hydrogen bond.
Yep.
Sodium
What?
chloride.
What's that?
Sodium chloride.
Sodium chloride. Sodium chloride would be ionic. Because think about it, it's going to be, you're going to have something that's going to be partially positive and something that's going to be partially negative interacting with something partially positive and something partially negative. Sort of like water, but
So like sulfur fluoride or sulfur difluoride or a molecule like that.
Yeah. Sulfur difluoride, yeah. That would be a good example. So if we had two of these guys interacting together, it'll be like this. And then the molecule will be favoring going in that direction towards the two fluorides, right? And so it'll be polar. So this guy would be partially negative, and this guy would be partially positive. The opposite of water, right? And so this guy would interact with the other fluorines up here. Okay, make sense?
Yeah.
The only thing different between the hydrogen bond one is that now you're not using hydrogen. Hydrogen is not the vehicle of that dipole-dipole interaction. And you're not working with one of the strong three, right? Okay. Okay. What about ion-induced dipole?
would be the carbon dioxide.
No, carbon dioxide would be induced dipole. That'd be CO2.
Oh, yeah.
So ion. So this means that you have to literally have an ion there. So if we had the sodium ion, and then we had CO2, right? So then that's going to induce. Yeah.
I see.
Okay.
So that wouldn't work like carbon dioxide with like fluoride with a negative charged ion because it wouldn't attract the electrons.
So what's going to happen in this case, right? This has that plus charge, right? So then the oxygens are going to be induced. So you're inducing the electrons to move towards that oxygen, right? Because that sodium is a plus charge, right? And so it's kind of like, hey, I'm positive. Come on. Bring those electrons over here, right? And so the oxygen, this oxygen is going to get those electrons, and then it's going to be induced in that direction. But that's only temporary because we know that those electrons are going to be pulled the other way because at some point this guy's going to get induced as well too, right? Because it's a solution of both.
But what if you brought, instead of a positive ion, a negative ion?
If I brought a negative ion, then in that case, it would be interacting with the chlorine because the chlorine's in the middle, and that's the one that's getting shortchanged, right? And so, and then in that situation, you'd have a slight interaction with that center rather than the outside guys. Okay. But it would still induce it because then it'll pull things towards the center in that case, right?
Right.
Push things towards the out. Now, I guess it would be pushing things out. So
yeah, I know what you mean.
Okay. So dipole-induced dipole. So that is kind of like it's like water and carbonated water. There you go. Okay. So because water is polar, it's dipole, and then you have carbon dioxide. Carbon dioxide is nonpolar, and so it's going to induce it. It's going to like that partial positive, and that partial negative is going to be inducing the carbon dioxide. Okay, are you with me? Yes, no, maybe?
Yeah.
Okay, good.
Mostly.
So you haven't tapped that yet. That's what you're telling me. Okay. Clear. So everybody got this down?
Yes.
Good. Okay, so now that you've got that down, let's see if you guys can use the knowledge. Okay, here's your question. Oxygen solubility in water is 3.2 milliliters per 100 milliliters of water. Carbon dioxide solubility in water is 81.0 milliliters in 100 milliliters of water. Explain the difference in solubility between oxygen gas and carbon dioxide. So solubility is.
Wouldn't the carbon dioxide with the water be dipole? So it's a weaker energy required to break it or disrupt it or whatever?
So you're saying the oxygen?
No, the carbon dioxide with water.
Okay. So you're saying with water. So let's think about this, right? So carbon dioxide has CO. And then oxygen gas, what is the chemical formula for oxygen gas?
O2?
O2, right? So it's also double bonded. Okay, so now look at the bond between, let's say, the O and the O, right? They're going to be exactly the same. There's no carbon to kind of offset things, to kind of take things from temporarily. And, you know, so these guys are going to be, the pull on them are going to be very, very even, right?
Mm-hmm.
So in that case, they're going to have a shorter, well, I won't say it. I'll let you guys think about it. So why do you think that? Because if you look at it, the oxygen solubility in water is much less than that of CO2. So solubility is a result of things being able to kind of dissolve in it or to be suspended in water, right?
Mm.
So like, for instance, we talked about salt solubility. Salt has a very high solubility in water, right?
Yeah.
So when we put sodium in there, the sodium ion goes in there nicely and all of that stuff, right? So which one is going to, in terms of solubility, based upon what you see in the numbers, which one is going to be more in solution and maintained in solution? The oxygen gas or the carbon dioxide gas?
The carbon dioxide.
Okay, so carbon dioxide is going to stay in solution better than oxygen gas. And so now, why?
Because it's an induced dipole.
So, but aren't they both induced dipole? They're going to be induced. Well, one is going to be dipole-induced dipole. And isn't the other one also going to be dipole-induced dipole?
Well, it's because wouldn't the wouldn't the oxygen for the water interact with the carbon, and then the hydrogen interacts with the oxygens on the carbon?
So you're saying the oxygens are going to interact here, and then the hydrogens are going to interact there. Okay. So, and then what's going to happen in this case?
The hydrogens wouldn't interact with the oxygens, but the oxygens would push it away.
Okay. So yeah, so in that case, you'll have your hydrogens that are going to be able to interact here, right? But you don't have anything that's kind of attracting the oxygen.
Yeah.
Is that what you're saying? Okay. Yeah. So, and in that case, and so you're also, if you think about it, right? Because this guy is positive, right? So that guy is positive. And so this guy, it's only going to get its negative temporarily. And also because that temporarily is going to be much smaller in the case of this situation than this situation, because the pull between carbon and oxygen is greater than that you see with the oxygen or oxygen.
Yeah.
Okay, good job. Or it's like the electronegativity, right? Okay. Okay. Good on time. Good. Okay. So you guys understand the difference between intermolecular forces and intramolecular forces?
Yeah.
Okay. So we'll see. Okay, so now when we think about this, right, a lot of this has to do with energy, right? It goes back to energy. So that concept of us going from, let's say, a solid to a, going straight from a solid to a gas in the case of carbon dioxide, right? And that has to do with energy, right? So we know that it's little energy to dissociate those dispersion forces, right? Compared to, in the case of water, where we're going from ice, then we go to liquid, then we go to a gas, right? So at room temperature, what is water? Is water a solid, liquid, or a gas?
Liquid.
Liquid. And so if we have dry ice and we let dry ice melt or sublime, then what happens in that case at room temperature?
I guess.
The gas.
Gas, right? And so that transition is a direct result of energy, right? And so kinetic energy plays a huge part in that case of the intermolecular forces. So to overcome those intermolecular forces, energy has to be put into the systems, right? And so, and that helps us understanding that at room temperature, what are these things going to be, right? If we have an idea of the intermolecular forces that are going to be involved, what can you predict, right? So like in the case of our diatomic molecules, right? We have a lot of diatomic molecules. So are they going to be polar or non-polar, or what's going on there? What would we expect them to be at room temperature in most cases?
Gas.
Yes, right? So most of our diatomic molecules, our diatomic elements are going to be gases, right? Because we know oxygen gas, nitrogen gas, and so this kind of helps us explain that, right? Because you don't have those interactions to kind of pull those components together. Those molecules aren't interacting in any way. Okay, does that make sense? Yep. No. Okay. So this is just basically showing you that, right? So as kinetic energy basically increases, right, we go from a solid to a liquid. And if we increase it some more, then we go from a liquid to a gas. So as we increase the temperature, or we can increase that energy that's put into the system, then that also causes the intermolecular forces to stop. You have less of them interacting, right? You disrupt those interactions, okay? So in that case, the intermolecular forces are going in the opposite direction, right? The more intermolecular forces you have, the more of a solid you're going to be, right? Does that make sense?
Yeah.
Yes.
Okay. So if we think about, let's say, water, right? So here we have condensation on the glass, right? Right outside of a beverage, or in the case of a lake, right? So fog on a lake, you can actually see the fog just sitting right above the lake, the water vapor, right? And so we can see the effects that by disrupting those intermolecular forces, that how it's going to affect the circumstances, like in the case of the condensation on the glass, right? Okay. So we can actually, with putting things under pressure, we can actually make gaseous butane into a liquid form, right? And that's by pressurizing, putting things close enough together that they interact, right? And so under the circumstances, we're adding pressure to the system to cause that interaction to be maintained. As soon as we open up that system to the environment, we know that butane will start becoming gaseous, right? And then you lose all the liquid out of your lighter. Okay. So you're familiar with the different types of intermolecular forces. Let's kind of give you some examples of them, right? So intermolecular forces, these guys are going to be weak interactions. So the interactions between the hydrogen and the chlorine in this case, right? Where intramolecular forces are going to be strong, right? That's between the bond between the chlorine and the hydrogen. Dispersionary forces, right, or London forces. So those guys are going to be induced. So they're only going to happen, they're going to be there temporarily, right? So they're going to form instantaneous and they're going to be disrupted instantaneously, okay? So here's an example. Well, these guys are going to be partially positive and partially negative just for a moment, right? And then it gets a little bit of an attraction. And then they're going to switch, right? And so those guys are going to be weaker interactions, okay? So the heavier molecules get, the more that they're going to have the ability to interact, right? The stronger those dispersionary forces are going to be, right? So the lighter the molecule is, then it's going to have, well, weaker dispersionary forces. Does that make sense? Yeah, no, maybe.
Yeah.
Okay, and that's because, you know, in the case of your heavier molecules, they have a lot more butt to them, right? They have a lot more electrons to sit there and kind of work with, to kind of shift around, to kind of get induced. Okay, the ones that are nice and lean and all that stuff, they only have a little bit, so they're going to be induced and they're going to be out just like that. So if we take a look at this table here, right? And so these are all diatomic molecules or halogens, halogen gases, or not all of them are gases. If we take a look at these guys, what is the temperature for freezing? The freezing temperature for in Kelvin? Ice freezes at what degrees Kelvin? Anyone?
Is it negative 173?
No.
I don't remember what the conversion is.
So how many degrees does in Celsius does ice freeze?
Zero.
Like 40 degrees Celsius.
So no. So 0 degrees Celsius.
Oh.
It's 32 degrees Fahrenheit.
Yes,
That's maybe what you're
right.
thinking of, Leah.
Okay. Well, you guys have been out of the lab too long. Okay, so ice freezes at 0 degrees Celsius. And then we know that the conversion from
Oh,
Celsius.
so it should be 273.
That's right, 273.
Oh, I got 73 right at least.
So we know that based upon what we know, so these are the melting points. Melting point is the point or the temperature where that molecule begins to melt, right? So, and then the boiling point are those temperature where things begin to boil and become vapor, right? So if you take a look at these values, right, we know that fluorine is a gas, right? Because its melting point is 53 degrees Kelvin, right? So isn't that significantly lower than freezing for us? So we know that if it's at room temperature, what would happen? Would it be a gas, solid? It's like
It would be a
liquid,
gas.
solid, or gas? What was that?
If it's at room temperature, wouldn't it be a gas?
It would be a gas, or it wouldn't be a gas?
It would be.
Yes, it would be gas. Yeah. So we know that fluorine would definitely be a gas. What about chlorine?
Also a gas.
It would also be a gas. What about
Very
bromine?
dangerous gas.
A dangerous gas, yes. Bromine. Would it be solid, liquid, or gas at room temperature?
Wouldn't bromine be a gas too?
So room temperature is what? Typically, room temperature is about 23 degrees Celsius.
I was gonna
Which
say
means-
28.
I like it cold. So 23 degrees Celsius would be how much in Kelvin? (273) plus 23?
Negative 250.
No, plus
Oh yeah,
Plus.
sorry.
273. What was it?
296.
Okay, 296. Okay, so its melting point is 266 degrees Kelvin. Okay, so it would melt at 266 degrees Kelvin. And then at 332 degrees Kelvin, it's going to boil. Okay, so which basically means it's going to become vapor. So would that be a solid, liquid, or gas?
Be a solid.
It'd
It
be a
would be a
liquid because it's slightly higher than its melting point.
That's right. So 293, so it's between the two, its melting point and its boiling point, so it would be a liquid, right? So we would expect this to be a liquid at room temperature. This guy, obviously, gas. Gas. Okay, what about iodine?
It'd be solid.
Iodine is actually a solid, right?
So
Because
when you buy like the iodine, it always comes as a liquid form. Do they just mix that with something?
yeah, they put it in solution to get it.
Mm.
Yeah, so it's an iodine. So when you actually buy real iodine, it's called sublimed iodine, and it's a solid.
Mm.
And then a statin is basically going to be a solid, right? Okay, so as we got bigger, right? So even though that all of these in all of these situations, all of these guys would be nonpolar, right? Every situation, but the dispersion forces got stronger as we got bigger. Does that make sense?
Yes.
Yes. Okay. So here we have group 14, group 14 compound. So we have methanol, we have tetra, hydrogen, silicone or silicide. We have tetrahydrogen. I guess that would be germide, and then we have tetrahydrogen tin. Okay, and so if you look at this, so this basically is the different periods, and then this is the melting temperature. Sorry, is it melting temperature? The boiling temperature of each of these. Okay, so minus 150 degrees Celsius would be our boiling temperature for methane. Okay, so what can you say about that in this situation? Based upon this curve. Nothing? Everything?
That like as the period, I guess the elements would be getting bigger too. The boiling temperature decreases because it's getting closer to zero.
So is it decreasing or is it increasing?
Increasing, sorry.
Yeah.
Increasing.
Okay. And so, and you could say that they're getting bigger, right? So those molecules are bigger than the ones that were before them, right? And so it serves that same trend that the halogens were showing us, right? Yes, no, maybe?
Yeah.
Yes, it does.
Okay, so I'm actually going to stop here because you guys are actually ahead of the other class by a slide. So, and try to keep you guys on track. So we'll pick this back up on Wednesday. Okay.
Okay.
And there's no
Okay.
lab tonight,
There's
right?
no lab tonight. Yeah, you guys get a break. Or at least one lab. We'll have a lab on Wednesday.
Okay.
Okay.
All right. See you on Wednesday, Dr. Henry.
You guys have a good night.
You too, Dr. Henry.